So, hi, ladies and gentlemen. I'm sorry I can't be here today, but I'm off doing training stuff for the county and probably having not that much fun, but maybe so. We'll see. But you guys are going to have an awesome time. So, you're going to learn about free fall today. And free fall just means something's being acted on by gravity. So, things that are important about free fall, just general concept, things of different masses or different weights, they still fall at the same rate. They still fall toward the ground with the same acceleration. So this really only happens at sea level, and if we completely ignore air resistance, hence if we had a feather and a bowling ball dropped at the same time, well, those aren't really going to accelerate at the same rate because the feather isn't technically in free fall. When we'll learn about forces next after we finish motion, but in free fall, only gravity can pull on that object. So there are no other things pushing or pulling. So if you look at the bottom of your screen down, or of this screen down here with this cannonball, the cannonball starts out the cannon starts out and launches this cannonball, and it follows this path and then falls back down toward the ground. While that cannonball is in the air, nothing else is pushing or pulling on it. So when the cannonball is being launched, it is not technically in free fall, but as soon as it has been launched out of the cannon, and my path isn't exactly right there, forgive me for that, but as soon as it's been launched out of the cannon, that cannonball is in free fall. So things in free fall can also be moving up, even if something's going upward. As long as the only thing acting on it, the only thing pulling on it is gravity, then that object's in free fall. Something else very, very, very important to point out. The gravitational acceleration constant at sea level with no air resistance, gravitational acceleration is 9.81 meters per second, or 9.81 meters per second squared, because we know those are our acceleration units. And that's always a positive value. Now, we might say that, according to our problem, however we set things up, that up is positive and going downward is negative. And all that really means there is that we have to say that our acceleration is downward in the g, or downward with a magnitude, a size of g. So that negative sign ends up going onto the g, not saying g is negative 9.81. G is always going to be your positive value, because you should have set your conventions for what's positive and what's negative in the problem to begin with. And really, we can take that formula that we learned, that kinematic equation we learned a couple classes ago, that our change in position equals our initial velocity times time plus 1/2 acceleration times time squared. And really, that's just going to say that if we're just dropping something, if something is entirely in free fall with an initial velocity of 0, then it's going to, then we can find its position, how far it's falling, just with this formula. But don't worry about that. We'll pretty much derive it every single time, we'll come up with that in our problems. So I don't know what happened with my pictures here, but really, you have this symmetrical path when things are in free fall. If we were to throw an object upward, let's say this is a height, we'll use y this time, of 0 meters. Let's say we were to throw something upward at a velocity v0, and it's going to follow this path, and it's going to go off the ground upward, and then it's going to fall back downward. Now, I'm only making it go a little bit sideways just because, but at this same height, at this height of 0 meters, you're going to have the same speed, except in the opposite direction. So you have this symmetrical thing. If we have some height here, let's say this is y1, then our velocity at this point could be v1, and our velocity on this side would be negative v1. So we have this symmetrical path along the same, along this whole thing. And in fact, if we cut this down the middle and call this side, say that this takes some amount of time, t1, to get up to the top of its path, then it's actually going to take the same amount of time, t1, to fall back down to the other side of the path, back to the ground. So let's see if we kind of understand this. At what acceleration does a 5,000 kilogram elephant fall to the ground? You have it? So it's just that same acceleration, 9.81 meters per second squared, downward. And then the same thing. The mouse falls to the ground, add an acceleration of g in the downward direction. Everything, as long as you don't have like much air resistance there, will fall, if nothing else is pushing or pulling on it, toward the ground at this same rate. It'll speed up toward the ground at that rate. So let's try some practice problems. We have this first practice problem where we're dropping a ball from a cliff, and we want to assume air resistance is negligible. That means there's practically no air resistance. We can ignore it. We want to know how long is the ball in the air, and then we want to know a few other things, but let's start with this part. So I'm going to start by drawing a picture. And I'm going to say that it was, 120 meters is what my paper says. So here's my cliff, here's the ground. Let's say this, and I'm going to use a little bit of a different convention here. Instead of x's, I'm just going to say these are y's because, hey, we're dealing with vertical motion. So this is going to be y equals 0. This is my initial position. Actually, no, sorry, that's my final position, my bad. So y final is going to be 0. And then my y initial, 0 meters, my y initial was that 120 meters. Now, we also know a few other things. We should know, like everything that's just falling, we know acceleration is going to be g. And in this case, I'm going to go ahead and say it's g downward. I'm going to say it's negative g. Then you could actually set this up a little bit differently, but we'll go over that when I'm there. So our next thing that I actually know is that this ball it's dropped. Because it's dropped, we know that our initial velocity is 0 meters per second. So what formula do we have? And we also need to know, we want to know how long is it in the air. So how long means time. So we need to find time in our formula. So if we look at our formulas and all of those kinematic equations we learned, then there's one that should stick out. And it's that, x final equals x initial plus v0t, blah, blah, blah. And I'm just going to change those x's to y's because that's just vertical position instead of horizontal position, and that might make a little more sense in this problem, and it might set you up for some better things coming down the road. So let's see, v0t plus 1/2, I struggle with multitasking as we all know, at squared. So some things I can do here. I can say, well, I knew my initial velocity was 0, so I can go ahead and say this entire term is going to be 0, no matter what time is. If I multiply it by 0, it's going to be 0. And I can also say that my final position is going to be 0. So that rearranges some things. But for now, I'm going to leave this 0 equals our initial position plus 1/2, and I can also plug in my acceleration. I can say that that is negative g t squared. So then if I move this term on the right to the other side, add it to both sides, then I can get that, y0 is equal to 1/2 gt squared. And then when I solve that for t is just going to be the square root of 2 times y0 all over g, and then I can plug in my numbers at the end. So square root of 2 times 120 meters, and I said 0 there, initial there. You guys know what I'm talking about. And remember, g is this positive 9.81 meters per second squared, because we've already plugged in our negative sign up here where we plugged in this negative g. We've already said it's going downward, so we don't want to do that again on accident. All right, so if I plug that into my calculator, I got 4.95 seconds. So it's going to take 4.95 seconds for that ball to fall to the base of the cliff. Okay, so let's try the next one. We have speed and velocity at y equals 0. Really, if I find the velocity, then I can just say, well, my speed's the same, but it's either up or down, because this thing is just, well, it better be going downward because this thing is falling. So I now need my final velocity. We don't know it. We knew that v0 is 0. We knew our y initial was 120. We knew our y final was nothing because it's fallen toward the ground. And we knew acceleration is negative g. Okay, so find your formula that has all those things. And it's this one, and I'm going to change my x to a y because we're dealing with a vertical direction. So really, I just want my final velocity. Initial velocity is 0 here. This should be pretty easy to do. So vf is going to be the square root of 2 times acceleration, negative g, times delta y. And remember, any kind of delta something, any kind of change in something is going to be final minus initial. So really, I want to have y final minus y initial. And y final, of course, was 0 because it's falling to the ground. So that's why when I eventually take the square root of this thing and I have a negative g, my y0 there, I'm also going to use a negative value for that. So you're going to be getting a positive value inside the square root. So you don't have to ever deal with any like imaginary numbers. That shouldn't ever happen. In fact, if it does, you know you probably did something wrong. So when we solve that thing, we get that we have a final velocity of, I have negative 48.5 meters per second. And if we wanted our speed up here, that's just the positive value, the absolute value of our velocity, because this negative just says we're going downward. All right, so let's look at speed and velocity at half of the distance. So really, we can just use that same thing. The only things that changed here, if we've already kind of derived this expression here for final velocity at some height, then all we have to do is use that and plug in different numbers, because instead of, let's see, so we've got square root of 2, really this whole thing is going to be equal to square root of 2g delta y, right? So that's what we can put on our next slide. We can say that at any point when something's falling from rest, our final velocity is going to equal the square root of 2 times g times delta y. And you can go back and solve that again. Everything will be the same except for this value that you plug in for our change in position. So instead of using, what was it, 120 meters for delta y, in this case, we're going to use half the distance, so we'll just use 60 meters. And when we get that, we get negative 34.3 meters per second. And our speed, of course, would be positive 34.3 meters per second. The last thing we have to do is sketch these graphs. I'm just going to draw the general shapes. You can go ahead and like figure out exactly what they would do, but our x versus t graph, or our y versus t graph, whichever we want to do, is going to be this curve. Oops, that should start at 0, my bad, or 0 slope, sorry. So we're going to have 0 slope at the beginning because we're dropping it from rest, and we know the slope of this curve is our velocity. For our v versus t graph, well, our velocity is downward the whole time, but we're accelerating at a constant rate, so our velocity is changing at a constant rate, and we can go figure out these values if we wanted. And then for acceleration versus time, we've got this negative